Hello and welcome to the I2I broadcast with me. I'm Heike, and today I want to talk about a very important topic, something that really goes close to my heart, which is atomic models. So it's a very scientific topic today, but it's one of the things that it's really the core of what we're teaching with Into Infinity. And today I want to give you a bit of an overview of what already happened in the history of humanity and what kind of models we came up with, and what kind of model we are offering today. So let's start. If it works. I love technology, of course. Okay, here we are. Yeah, how does the atom look like? Most of us are familiar with matter. Yeah, it's surrounding us every day. But what kind of models, we know about, you learned probably in school, but where is actually the first idea coming from? I mean, this is what we pretty much know today. We have like the nucleus in the center with protons and neutrons, and then we have these electrons outside, and we know actually 99% of the atom just consists out of space. And the electrons negative, they're in this electron cloud. But who actually came up with the first idea? Yeah, what is the world made of? And I'm in India right now, so that's why it's so beautiful that I'm starting here. It actually really goes back to ancient India. And Acharya Kannada, I don't know if you speak it right, but Acharya means teacher and Kannada means smallest particle. So actually, he was somebody who was thinking about the world and if you can divide it into smaller and smaller particles. And the way he was doing it, he was just looking at things, and he was looking at sand, and he was looking at every grain of sand and seeing how you can divide it further and further, and came to the conclusion at some point it goes out of our perception, but the nature, the reality needs to start from somewhere. And some people consider him, therefore, the father of atomic theory. So it's as old as 2,600 years from the 16th century BC, even though that's not quite sure. And he is also the founder of the Vaisesika philosophy, which is one of the six Indian philosophies. And in the sutras it says, a substance without parts must be the limit, and this is the ultimate atom. So obviously the whole philosophy is built on that idea that nature must consist out of the smallest particle that is indestructible. And further on, when we go to the Greeks, it's a big question if they may have had that knowledge from ancient India. But in Greece, it was Leucippus of Miletus and Democritus of Abdera, who also studied the world. They call it the atomos, and that's actually where the word atom comes from. Yeah, the smallest particle, and something that, again, cannot be divided into smaller parts. A few years later, in 427 to 347 BC, we have Plato. Even though he's not mentioned very often in the history of atomic models, he's been studying the 5 Platonic solids, which always refers to the smallest or the most regular forms of space, which he often was relating to the 5 elements as the foundation of reality. So in a sense, kind of an atom as well. And I mention it here because it's really important when it comes to our model of the atom. So just keep that in mind. But if you're thinking about modern science, now here we start somewhere completely different, which is John Dalton in 1803. So about 200 years ago, really, that's when the scientific movement started with the atom, and he suggested a solid sphere model where he came from a chemical point of view, and he realized that there are certain reactions happening, but they're happening in very defined whole number ratios. And he came to the conclusion that all atoms of the same element have to be the same, that different elements then vary in size, and that they're indestructible. But he couldn't get further than to just thinking about spheres or different kinds of shapes, but he didn't really know how it was looking inside. We have then in 1904 J.J. Thompson, who came up with the plum pudding model. And he was the first one to discover actually that there is charges in the atom. So he's considered the whole atom to be positively charged, but then there are these other charges, negative charges, and he was the first one, therefore, to discover the electrons. So that basically this thing is not just matter, it's having charge, and these electrons, they're in kind of like a plum. You just think about a plum, and in that plum you have these holes with electrons inside. So that's why, I don't know, the plum pudding model. And built on that actually was his student later on, was Ernest Rutherford in 1911, and he proposed another model. He was going another step further, which is the nuclear model, because he was working with gold. So he was shooting like really intense alpha particles into gold, and he realized that actually most of these particles would go through, which basically meant that the atom is mainly empty space. And sometimes it would reflect that indicated that actually the atom consists also out of a nucleus, which is positively charged, while he suggested that the atoms somehow orbit around outside, even though he didn't know exactly how that really worked. But nevertheless, after that, we got Niels Bohr in 1913, and he proposed a planetary model, also called the Bohr model, which is really, really famous today, especially when it comes to chemistry and the stuff you learn in school. And he proposed that actually these electrons, and he kind of found a relation to the planets, just like the planets are orbiting around the sun in a similar way. I guess he figured maybe the atom works in the same way, which is quite interesting, because that all goes back to Johannes Kepler, how he would describe the solar system and how actually all of these planets form very defined ratios. So anyway, he was going to the atom, and he said, well, there are these electrons and they are in these very distinct shells, and they don't exist in between, which means that actually the electrons themselves are quantized. Now, quantized means that it's something like a package, and then it is emitted, but then in between it doesn't exist. Like there's another package and another package and another package. So this quantization of the model of the atom, was really important. But obviously, even though we are using this right now, still in school, it's not 100% accurate. So from here, we're coming to a complete different guy, and he's, probably a lot of people don't even know him, but this French scientist, Louis de Broglie, in 1924, in his thesis paper, came up with a pilot wave model, which is different to the Bohr model, in that sense that in the Bohr model, it was thought that the electrons are particles. And he came up with the idea, actually, the whole atom can be seen also that these electrons are working in a standing wave. So these electrons, still thinking in particles, would move in a standing wave, which underlined the idea that nature can be seen deterministic, and in a deterministic way, which means everything has a cause and effect, everything can be predicted in a sense. And what's amazing about this as well is that these standing waves, they actually follow musical ratios. From the first shell, the second, the third, and so on. You can actually predict the musical resonance, the octave, the fourth, the fifth, and so on, which is really beautiful when I go back to, let's say, the planetary orbits and Kepler and the whole idea of music of the spheres, which describes how also planets move in certain ratios that actually can be represented in how we perceive music and how the musical laws work. However, this model got taken over as well in 1926 by Erwin Schodinger, and he came up with the quantum wave model, where he was proposing that yes, electrons behave like waves, but these waves they are happening in a cloud of probability, which basically means you cannot actually say exactly where they are. There are some areas where they seem to aggregate more than others, like you see in this picture over here. Certain fields, just like these shells, you can see these waves more, and other shells you don't, or the spaces in between, which led to the idea of the Copenhagen interpretation, which is very different to what the Broglie suggested, which is basically at the atomic level, it's all chaotic. It doesn't make any sense, yeah? And then out of this chaos, somehow certain laws are being built upon, and then the laws of the macrocosm is different to the quantum world, which has been a big problem, and is still finding a solution today, how you can actually unify the big world with the quantum world with one unified theory. So here, obviously, the ideas changed, and that the quantum model showed that, yeah, probably somewhere the electron must be. And this goes very nicely with Heisenberg, Erwin Schrödinger in 1927, who also suggested the mathematical equation for this and called it the uncertainty principle, which basically suggests that you cannot find the speed and the location, or the acceleration and the location of an electron at the same time. So you can either say, okay, the electron must be there, or this is how fast it's moving, which is very, very contradicting to what we perceive, obviously, on our scale of existence. But it was underlying the idea of the quantum wave model, that actually there are certain regions where these electrons obviously appear, and certain regions they don't appear, but we cannot really nail it down to be for sure. It's just like a 90% chance, let's say, these electrons appear in certain areas. And the whole idea was the electrons are actually like particles with wave behavior, just as we see light. We have this whole idea of wave-particle duality today, which is still really weird, a really weird concept to wrap your head around. But basically what it means is that we have quantized energy packs, and somehow these energy packs work really as waves. So where does this lead us today? It leads us to the idea of orbitals, that actually these probability areas, they follow certain symmetries. And that's why here geometry comes in, because these orbitals, we call them S, P, D, and F. They're actually only 4 that happen in different shells and different combinations. But if you look at them right now, we have simplified it, because obviously it gets quite confusing when you see all of it at once. But S orbitals pretty much just look like spheres. So this is more the geometric interpretation. So even though maybe this electron can be determined or localized at a certain point, it cannot be the speed as well, just as I said, yeah. So basically what it means, in that sphere, this electron has a 90% probability to be located somewhere there. And the same goes with the p orbitals. While this looks a bit different, it basically, it's like a line. This is how we see it, yeah. So on one end you have an electron, and another electron can be found on another end, yeah. So the endpoints of a line. Also, it's this is called spin up and down, because 2 orbitals can now be found in this p orbital as well as in the s orbital too. So which means that they're always somehow opposite each other. And then we have these d orbitals, and the 2 first ones there already show us, they look like squares, while the last one is actually a torus field. So if you've seen any of the other videos, we introduced this a lot already. So the dot and the circle making this torus field, which is like an electromagnetic field which you see around the Earth as well. And then when we come to the f orbitals, we have hexagons. So there are geometries: sphere, line, square, and a hexagon, while there's also a double torus and something that we would see as a cube or a star tetrahedron. Yeah, this is really going into geometry, but this is the amazing thing about it. What we suggest is that when we're taking this model, which you learn pretty much in university, which is the orbital model and the different S, P, D, and F types, you can actually translate this into geometries. And if you think about it in geometries, then a different image can emerge. Thinking about, let's say there is this energetic wave coming in you call electrons, but they're limited by a certain space because it's not just complete chaos. There's a chaos, but this chaos is limited through something, which it seems like it might be space. So what do we suggest then? Going through just the last few models, the Bohr model, which is the planetary model, which is very, it's a predominant model that we learn in high school with these shells, and it also makes sense if you think about chemical reactions and so on. Then we have the quantum model, which shows it more in 3D, which is p orbitals. Like these are the 3 p orbitals coming together. And what we do, and this is really nothing new because this is something that it's already recognized, that these orbitals follow certain symmetries. And in our model, we call this atomic geometry. We just translate this orbital model into a spatial model. So how would the space look like if we don't concentrate on the energy, and I'm just calling it energy as in terms of whatever there is, the matter, the electrons, compared to what is the container, something that contains this, this apparently chaotic structure. And where does it lead us? It leads us to this video that we made. And just have a look. It's in German, so. Yeah, this is basically the electron.
Wasserstoff.
And it starts with the s
Helium.
orbitals and goes through the whole
Lithium.
periodic table.
Beryllium. Neon. Natrium.
This is where the p orbitals
Magnesium.
come in.
Argon. Kalium. Calcium. Eisen. Nickel. Kupfer. Zink. Krypton. Rubidium. Strontium. Molybden. Palladium. Silber. Cadmium. Xenon. Cesium. Barium. Neodym. Europium. Gadolinium. Ytterbium. Iridium. Platin. Gold. Quecksilber.
So yeah, this was our quick model and that we've been working on thanks to our animation designer Baptiste Vandel, thank you. So yeah, this is an atomic model that is based on geometry instead of looking at the energetic side, looking at the space. So I would like to just make a quick conclusion here, and we've been going through a couple of different models. I'm not going to mention all of them, but pretty much we started with the plum pudding model, where the idea of, there is a negative charge, there's a positive charge, but it wasn't really determined if it's a nucleus or something around. But the Bohr model then basically showed us that there's a nucleus inside and we have these very distinct shells, and these are quantized, and that's a very, very important part to understand. There is somehow this quantization, and I always like to see, like, think about a movie, no? And every movie has a frame, and between the frames you have this thing called black space, but you don't see that normally in the movies because it's so quick. But at the same time, it happens also with matter, no? You have the idea that actually all matter is quite solid and very fluid, but on the quantum level it's actually not. Yeah? So from the Bohr model and this quantization, we come to the Pilot wave model, which suggested that actually these electrons work with the standing wave, and that standing wave works with music. In that sense, that's been very beautiful to show it's working like waves, like energy waves, not just like particles. Then later on we have this Schodinger wave model, which suggested that this is actually happening, this wave-particle behavior is happening in certain orbital areas, which we come then to these SPD and F orbitals, which goes together with the Heisenberg and Copenhagen interpretation that we don't know exactly where these things are and how fast, where they are at the same time. and there seems to be this chaos. This is currently our scientific understanding, that everything of reality emerges out of chaos. Yet, what we like to do with our model, and there are different other models from other people slowly coming to the surface now as well, which is very beautiful, like the MCAS model, I didn't mention it before, which is also based on, on geometry in a sense. We're coming up with a model that goes back to the ancient Greeks, because that model is based on geometry, it's based on the space, and looking at the whole energy levels, not the actual energy levels, but looking at what kind of space, what kind of symmetries they are creating. And the Platonic solids and the Archimedean solids from the ancient Greeks come now into play, and they show us this beautiful architecture that is completely in line with some of the ancient ideas. And the idea that, no, it's deterministic actually, that the reality is built upon something that has a cause and effect and can be predictable. It follows a certain plan, you could say. And in that sense, it also is in line with more of the pilot wave model, because it also follows the musical resonances, as well as the idea that it can be seen as a wave model that is just held in place by the geometry of space. So that's a thought to think about. So, yeah, what I'd like to just mention now, because obviously I'm just going to summarize this whole thing in a bit, but before I do that, I just want to mention I got these two amazing courses coming up that are up for beta testing. So if you want to know more about what we're doing and getting into the topic and also applying geometric thinking in your everyday life to influence your life, to change and shift the way you think about life and yourself, I got a first course happening with Into Infinity facilitator Catherine Jeryomenko from Germany, and this is actually in German. It's called 40 Innovation Mastermind, and it's more of a business course which helps you to use geometry and dimensional thinking to change your perception of reality, as well as getting into your intuitive creator, getting into the idea that you can lead through mindfulness. So we have a couple of different technologies and tools that we're using in this. Well, we're gonna actually make a 4-week business course out of this, but this beta workshops are just 3 times 2 and 3 hours. So if you'd like to join us, we have still a few places available, which is on 25th, 26th and 27th, and it's in German. And the second course, if you just like to really wrap your head around what is universal geometry, where do I start? Because that's really the biggest question I always hear from a lot of people in the last couple of years. There's so much to explore in geometry, but where do I start? And this course I have developed because I want to give you the absolute foundation of universal geometry, where to start, how these symbols, such as the flower of life, the seed of life, Vesca Pisces, Trinity, Metatron's cube, Platonic solids, how are these shapes all linked together? How does it describe where we come from, and how matter is built up to the atomic geometry? So if you're interested to help me test this course, I have a beta test planned on the 9th, 10th and 11th of October. And for both courses, obviously, because we'd like your feedback, you're gonna get it for a very, very special offer. Right, in that sense, I hope you enjoyed a lot. Let me just go back to here. There you go. So, to summarize, what did we learn today? It was quite a very quick, going through the history of the atom, and we can go, of course, much more in detail, because the whole idea of wave-particle duality and what happened with the geometric view, what happened with also the philosophies behind it. We're trying actually to go back to these ideas that there is indeed a bigger meaning behind reality. It's not just chaos and randomness, and there is a sense of, there is a plan that starts to evolve and that is at the foundation of reality itself. So we looked at the ancient India, that they were already there, just with obviously more a philosophical standpoint of view. They didn't have the experimentation, because obviously you cannot get into the atom from here. There are certain boundaries. to the ancient Greeks who started to come up with the atomos, yeah, that's where the word originates from, to Dalton with his chemical reactions, getting closer to the idea that there is a very defined small unit which has been developed more and more, finding the nucleus, finding the electrons, and then it gets a little bit fussy. Is it a wave? Is it a particle? What is it? Well, maybe it's both, or maybe we can look at it through the eyes of geometry, and this is where our model comes in, which is very much in line with musical harmony, geometry, the planets, the cells, and spiritual thought as well. So I hope you enjoyed this broadcast. Yeah, if you'd like to know more, we're probably going to do a much more in-depth course about the atom, and hopefully, yeah, get to know the atom through playful creativity. Yeah, so you're building these things, you hold it in your hands, and therefore understand also how, yeah, certain reactions can take place. Yeah, through 3D thinking. I hope you enjoyed this. I said it already, and I wish you a great day. Next time I'll talk about, yeah, I talk a bit more about atoms. I think it's atoms and the periodic table. Not sure. Have a look. Until then, so much to explore.